So we are happy to have today Umberto, who will tell us about some types of periodic revolves and their role in four-dimensional symplectic topology.
Thank you, Pazit, for the introduction. Thanks to our organizer for the invitation. It's really a pleasure to participate again in the Zoominar. Today, topic of the talk is not types of periodic orbits, in particular periodic Hebb orbits. Knotted structures in dynamics is a theme that goes back a century and a half ago at least, with work on hydrodynamics by Helmholtz, Lord Kelvin, and so on. So this is really an old topic. Vorticity lines are preserved under the flow of several flows in hydrodynamics. So this is long known to be an interesting connection between dynamics and topology. And today, so the topic, the motivation for this topic is to see what can be said, explore what can be said in the context of Hamiltonian systems, making use of holomorphic curves and modern techniques from symplectic topology. So let me start with, say, one question, which I think it's open-ended and also interesting. Given a symplectic form manifold, say with contact type boundary, is there a symplectic invariant? For instance, a symplectic capacity. That can be read from actions of links of boundary characteristics with special properties. So loosely speaking, we'd like to read symplectic invariants from periodic orbits of a particular knot type. Is that possible? I mean, I think this is far from, I mean, this, I don't think that the community has addressed this question. This is, today I will explain a couple of results which say that yes, there is at least one example of such a symplectic capacity. And I think it would be interesting to have some kind of Floer theory that would be filtered by the knot type or link type of periodic orbits. Holomorphic curves are good for reading knots in low dimensions. They're good for reading knots up to concordance because if one is lucky, one gets holomorphic curves which are embedded in cobordism, in symplectic cobordisms. So the concordance type is more of a property which would be within reach. The knot type is quite difficult, and I think it's a challenge. And probably one can say something. So another question which I think is interesting is can the transverse knot link types of the periodic Hebb orbits be used as a measure of the topological complexity of a Hamiltonian flow or Hopf flow. So here one could try to use the knots and links that we see on the dynamical system, a three-dimensional flow, to try to mathematically propose some kind of measure of complexity of the flow. And I think this can also be somewhat hoped for in certain cases. And so these are, let's say, the two guiding questions for this talk. Now I have to make sure I can make a new page. So this question about the complexity goes back to G's, even back further to Berman and Williams on their groundbreaking paper, I would say, on the knot types of the periodic orbits which show up in the Lorentz attractor. Edtmair and Grist proposed questions like this in the context of Hopf flows. Birkhoff, I mean, one could interpret certain, say, statements by Birkhoff as instance of such questions in the context of the planar restricted circular three-body problem. For instance, Birkhoff was already aware that it was not so easy to find direct orbits for subcritical energy levels, in the sense that the orbit would go, the projection of the orbit to configuration space would be a simple loop that goes in the same sense of rotation of the two primaries. That would be a direct orbit. Our moon is direct. Birkhoff developed his shooting method, nowadays called Birkhoff shooting method, to find retrograde orbits. These would be, say, orbits which, when you project them to configuration space, they would go around the heavy primary in the sense of rotation against the sense of rotation of the primaries between themselves. Many moons in the solar systems are retrograde, but our moon is direct. It's quite amazing that so far there is no proof of a direct orbit. So for arbitrary energy levels below the first critical value and arbitrary mass ratios. Such an orbit would, after Leavitt-Witte regularization, would lift to an orbit of a Hopf flow in S3, which would be unknotted. And unknotted orbits are going to play a very important role in this talk. So it's the quest for a direct orbit for subcritical energy levels can be thought of as quest for unknotted periodic orbits of a special, say, so to speak, in a special position, so that they project down to configuration space as an embedded, as a loop without self-intersections. So these kinds of questions are also connected to finding orbits with a prescribed knot type in a certain special position. And I already mentioned Helmholtz, Lord Kelvin, in the context of hydrodynamics, and so on. All right, so basically we're trying to explore what's the role of periodic orbits of a given knot type, what's the role of the knot type in low-dimensional symplectic topology and dynamics. All right, so let me focus on the first question. So first half of this talk, I would like to focus on the second question, meaning complexity and knot types. Okay, so the Hopf flow is this is the simplest flow from this viewpoint. there is exactly just one knot type. Every orbit of the Hopf flow, think of it as two harmonic oscillators with the same period. So that otherwise said, think of the round three sphere sitting inside R4 as an energy level. Every single periodic orbit has exactly one knot type, which is the simplest knot type you can think of, which is the unknotted. So, sorry, what happened here? Sorry about that. Okay. So every orbit.
We can't see the screen.
Okay, so let me share again. Something happened. So every orbit is a Hopf fiber. Hopf fiber means the unknotted with self-linking number. -1. Okay, so this means that these knots they span a disk, an embedded disk, and if this disk can be chosen so that the characteristic foliation, meaning the intersection of the contact planes with the disk, has one tangency at the center and otherwise intersect the disks transversely, forming a foliation which is of radial type emanating from the center. So here's a periodic orbit, gamma, right? And that's the characteristic foliation. That's what it means to be unknotted and have self-linking number -1. That's how the contact structure looks like with respect to this disk. And there is a very nice theorem. I like this theorem very much, due to Hopf, Vysotsky, and Zander, stating that every Hopf flow on the standard contact 3 sphere must have a periodic orbit, which is a Hopf fiber. So in other words, a Hopf fiber is part of the minimal dynamical structure that a Hopf flow in the tight 3 sphere must have. Okay. So in some sense, that's a meaningful question. What's the minimal? So is there a link that always has to be there? And so an unknotted orbit, unknotted as a periodic orbit, I mean, right? And an unknotted periodic orbit self-linking -1 has always to be there. But then one might ask, is this the minimal structure? Right? So is there a Hopf flow on the standard 3 sphere that has this periodic orbit which is unknotted self-linking -1 and nothing else? And we know that the answer is no, right? There are other orbits, other periodic orbits as well. And so the minimal structure is conjecturally more than this. So conjecturally, one would say that, at least I would say that every Hopf flow on the, maybe you should say standard instead of tight, the same thing, but on the standard contact 3 sphere must have a pair of periodic orbits forming a Hopf link. So what's a Hopf link? exactly a pair of periodic orbits which are transversely isotopic as a pair of periodic orbits as you see them in the Hopf federation. So they are unknotted, they are linked, but not only that, they are transversely isotopic to a pair of Hopf fibers. Okay, both would have self-linking -1 and so on. So as far as I know, there are no examples of Hopf flows in the tight 3 sphere which don't have this structure. And this seems to be a pretty hard question. Also, with genericity, I mean, if you assume the flow is generic to make life easier, that's not easy to answer. But there are no examples without such a structure. This structure is, in some sense, lying at the foundations of symplectic topology. When Poincaré stated his last geometric theorem, later proved by Birkhoff and now known as the Poincaré-Birkhoff theorem, he found, so he stated this theorem because he found in certain situations in the planar restricted circular three-body problem, Hopf links, right? Hopf links which were made of direct and retrograde orbits. And these links would be spanning annulus-like global surfaces of section for the flow. And Poincaré stated his theorem precisely to study the return maps to these annuli. So the Hopf link is there since the beginning. Of course, we know that the Poincaré-Birkhoff theorem is what motivated Arnold to state his conjectures on fixed points of certain diffeomorphisms, which were later called Hamiltonian diffeomorphisms, and that motivated Floer theory and so on and so forth. So this is really the Hopf link is really a part of the, say, foundational story, I would say, of symplectic dynamics. And yeah, so there are examples, right, with only the Hopf link. Everybody knows this one. So the irrational ellipsoids. These are Hopf flows on the tight 3 sphere, which have this pair of periodic orbits. They form a Hopf link, and there's nothing else. No other periodic orbits are there. Let me keep an eye on the time. Okay. Of course, a Hopf flow on the tight 3 sphere, which has only the Hopf link as the periodic orbits, doesn't have to be that simple. We know that as well by now. That's these are these famous examples by Anosov-Katok. Right, one can construct these Hopf flows in such a way that so you have this Hopf link of periodic orbits, you have nothing else. Both orbits, they span disk-like global surface sections. I'm going to draw one of them. And the return map is epsilon. Oh, sorry. The return map is a pseudo rotation. The return map is a pseudo rotation. You can even do that in such a way that the metric entropy of the Liouville measure is positive, right? So from a dynamical point of view, just because you have only the Hopf link doesn't mean the flow is simple, because, well, we don't understand pseudo rotations. That doesn't. So this means that we still have a lot to learn here. On the other hand, there is a theorem by Edtmair and Grist stating that there exists real analytic contact forms on the standard S3 such that every transverse link is simultaneously realized as periodic Hopf orbits. When I say transverse, I mean transverse to the contact structure. So this is pretty crazy. I mean, so you can draw a line here, right? This line represents complexity from this point of view. In one end of the spectrum, you have the Hopf flow. So only one, right? Only Hopf fibers. The flow is integrable, it's totally periodic and nice, easy to understand. At the other end of the spectrum, you have these examples by Edtmair and Grist, right? So every transverse link is there. And the question is whether we can explore what happens in between these two extreme cases in a mathematically meaningful way. So it would be nice to understand conditions which allow us to navigate this complexity line here. And the result of Hopf, Wysocki, and Zander says that no matter what you try to do, there is always the Hopf fiber there. Conjecturally, I would say that there must be always a Hopf link there. Okay. So to make this question meaningful, the question about whether can we so to speak, identify conditions that allows us to navigate meaningfully from very simple flows to very complex flows. From this point of view, we need to look for conditions, right? So are there symplectic geometric conditions that, when imposed on a contact form, restrict the knot types or let's say the transverse knot types realized by the periodic Hopf orbits. Okay, so we know a few conditions, for instance, convexity. It's not a symplectic condition. More generally, you have dynamical convexity, which is the symplectic version of convexity defined by Hopf, Wysocki, Zander in the end of the 1990s. Okay, so sorry about that. I don't know. I mean, now I don't know how to stop this from happening. Okay, so I'd like to explore what dynamical convexity has to say about these questions, about whether dynamical convexity does restrict the knot types or not. And before stating the result, let me state a conjecture here, or maybe another conjecture. Maybe let's make this a question. Does dynamical convexity of the contact form imply that the Hopf flow is right-handed in the sense of G's? Right, so right-handed here. Right-handed here means that every single link of periodic orbits spans a global surface section, right? In particular, so this means that every link of periodic orbits spans a global surface section. So in particular, the all fibered links. So if this is true, that would be a huge restriction that dynamical convexity imposes. And of course, it's almost unbelievable that such question would have affirmative answer, but there are no counterexamples. So yeah, so that's I think it's a fair question to look for an answer. We have other kinds of results about this. So let me just say, before stating one, let me just say that Hopf flows, that must be called Hopf flows on the standard S3 are into one-to-one correspondence with Hamiltonian flows on star-shaped energy levels in R4, right? So these are energy levels which are compact, smooth, and so that if you, for some point in the middle, if every ray issuing from that point is going to intersect transversely and only once the hypersurface, okay? So these energy levels are the Hopf flows on S3. And we are going to call such a domain, so these they bound domains, right? Such a domain is going to be called, so it's always with the standard complex structure. Such a domain is going to be called dynamically convex if every closed characteristic has Koenig-Zünder index at least 3. That's a definition by Hofer, Wisniewski, and Zender. 98. Okay. So it's nice that convexity implies dynamical convexity, meaning that if you draw a convex energy level, you have this property. Koenig-Zünder indices are always at least 3 when measured with respect to a global trivialization of the context structure. So now I can state one result, which is in collaboration with Pedro, Salomão, and Richard Siefring. So here, omega is a dynamically convex star-shaped domain. if gamma, so that's a boundary characteristic. So it's a closed boundary characteristic. This means that the closed orbit of the Hopf flow in the boundary. If gamma is symplectically slice knot, then it is a Hopf fiber. So this means unknotted self-linking -1. Okay. So that's one restriction that dynamical convexity imposes on the knot types. Symplectically sliced knots, which are not Hopf fibers, are not allowed. That's the main take. And so in particular, so the knots, now I'm going to refer to Rothson's table, right? I'm going to refer to knots as they are, say, depicted as they are written in Rothson's table. So 820, 946, 10, 140, and 10, 155. I'll say a little bit more about Rothson's table. Admit transverse representatives that cannot be realized as periodic Hebb orbits. Okay. For a dynamically convex Hebb flow on S3. So there are knots which are not allowed. So if you go back here to the complexity line, dynamical convexity, at a certain point, you cannot go beyond. I mean, if you want to see certain knots, 820, 946, and so on, right? There are many, many, many other knots like this, which are symplectically sliced but not Hopf fibers. At some point, you cannot go beyond this complexity level if you want to keep dynamical convexity. So somehow there is a restriction. So let me try to draw one of them. I mean, it's pretty crazy. So if you go like this, and then what happened here? Here. Okay. That's the 820. So 8 means that there are 8 crossings. 20 is some ordering of this table. So this knot cannot be realized as a periodic Hebb orbits for dynamically convex. I mean, some so to speak, representative of this knot, which is transverse, cannot be a periodic orbit. So there are many, many, many other. I mean, I gave just 4 examples. There is another result, which is also in collaboration with Salomão and Siefring, stating that any, of course, assuming dynamical convexity, any finite collection of Hopf fibers given by periodic orbits of a dynamically convex flow on S3 forms a hybrid link, meaning that actually more can be said. They span a global surface section, meaning, of course, high genus. Right. So these are restrictions on the periodic orbits, on the knot types, and on their presentation, how they can be seen inside the flow. All right. So let me just say a few words about this. Okay, so there is a notion, so some ideas, right, for the proof. There is a notion of quasi-positive link. So these are links which can be represented as braids, and these braids can be written in terms of the positive Artin generators of the braid group. So there is a notion there, and there is a result by Rudolph saying that these links are smoothly isotopic to transverse C-links. So whatever this is, I mean, there is an argument which is based on results by Eliashberg. So results of Eliashberg can be used to prove that these guys are, say, intersections of, say, if you identify R4 and C2, these are intersections with S3, between S3 and some complex curve, C. Right? And now using results by the famous paper by Bikalev and White on intersections, on positive intersections of homomorphic curves, these guys are actually symplectically null homologous. So this means that inside S3, I mean, I'm going to draw the link here. Inside S3, they span a symplectic surface. So inside D4, so D4, S3 is the boundary of D4, right? This is the symplectic surface. Finally, there is a result by Gadgil and Kulkarni, saying that the slice in the symplectic case, and if you see a symplectic slicing surface like this, the symplectic genus is equal to the slice genus. Okay, so this means that, what does it mean? It means that if we can find slice genus zero links which are quasi-positive, then they are symplectic slice genus zero, and so they are obstructed by our result. They are obstructed from appearing as a periodic orbit of a dynamic convex Hopf flow, unless they are already unknotted, have self-linking number -1. Okay. So let me sketch the proof. So we consider our star-shaped domain. Here is our link, our knot, which is symplectic slice. So there is a D2 here, where the symplectic form is positive. And the idea, so the technical part is to say, I mean, this guy here has collision index at least equal to 3, which means that the asymptotic operator allows for holomorphic curves to approach this periodic orbit very fast, right? The approach of the holomorphic curve to a periodic orbit is governed by the so-called asymptotic operator, which is, say, it plays the role of the Hessian of the action. And so we have enough space to reduce the index so that it's equal to 3, so that the space of planes would have dimension at least exactly equal to 2. And then there is one quite technical aspect of our paper is that now we can realize this guy as a holomorphic plane for with simplexization type end. And we can do that in such a way that the asymptotic approach is allowed, is the fastest possible. So it means that if we put an exponential weight here so that the collision index is effectively equal to 3, this plane that we produce, which comes from this symplectic slicing disk, is fast enough. So now we can try to foliate the whole domain, right? And we can choose a mark. So we have a moduli space. We can choose a marked point. Consider moduli space a marked point. So the dimension goes from 2 to 4. And we can push this marked point near the boundary. And what happens is that by compactness, one can argue that this plane is going to eventually completely lie inside the simplexization part of the symplectic completion. And now, I mean, this plane is started embedded. Intersection theory tells us that it's going to stay embedded. So when it's completely inside the simplexization part, it's going to be projecting to an embedded plane. So the orbit has to be unknotted. So that's basically the argument. All right, so now I'll try to use the last 10 minutes to talk about symplectic invariance. I mean, so I use most of my time, I guess, to talk about complexity, topological complexity of periodic orbits. Now I'm going to talk about symplectic invariants, which come from knot types. If there are any questions, please just interrupt me. Okay. So now I'm going to state a theorem which is collaboration with.
Sorry, I have a quick question.
Sure.
Can you say again what you mean by fast convergence fast enough? Somehow that implied that the whole disk was in the symplectization end or something? I didn't understand that point.
So you see the collision index is at least 3, but it could be very high. So if one somehow takes this symplectic disk and produces a holomorphic plane out of it, if we just take this plane as it is, it's going to lie on a potentially very high dimensional moduli space. But if the approach is fast enough, right, we can cut the Fredholm index down by putting the appropriate exponential weight. And now we're going to be, so this means we're going to be picking out inside this high dimensional moduli space a 2-dimensional subspace of planes. So we have to produce planes with fast enough approach, right?
Thank you.
Just like in Morse theory, I mean, we have a Morse trajectories approach. So let's say you have a Morse function. A Morse trajectory approaches a critical point according to an eigenvalue of the Hessian, a negative eigenvalue of the Hessian, for instance, if it comes from below. So, you know, the unstable manifold has a certain dimension, but if you're lucky enough to pick a trajectory which goes fast enough, which means asymptotic to a low enough eigenvalue of the Hessian, then you can cut with an exponential weight and produce inside that unstable manifold a certain submanifold of trajectories. But one has to be lucky or say one has to somehow consider this fast Morse trajectory. That's the same picture here.
Okay, thank you. I understand.
Okay, so to talk a little bit about knot types and symplectic invariants, let me consider a four manifold, symplectic four manifold, W. So you can define an invariant C Hopf of W omega to be the supremum of A Hopf. I'm going to tell what that is. A Hopf of omega 0, where omega 0 sits inside R4 omega 0, is a dynamically convex domain, star-shaped domain, and symplectically embeds into W omega, okay? And A Hopf is the infimum of actions of closed characteristics in the boundary which are Hopf fibers. So it's a typical min-max or max-min in this case, right? For each star-shaped domain, infimum of actions of Hopf fibers, of periodic orbits or Hopf fibers, and then you take the supremum of all possible embeddings of a star-shaped domain inside our symplectic manifold. And the theorem states that this C Hopf is a, I guess nowadays we have to say normalized symplectic capacity. Okay. So this is similarly, I mean, it seems to be a new symplectic capacity, right? And but we can actually prove also that if the symplectic four manifold is actually equal to our star-shaped domain and dynamically convex, then C Hopf is equal to C1 ECH. So the first ECH capacity. So what's interesting about this is that one can prove this is a capacity without using any Seiberg-Witten theory. That's a purely holomorphic curves proof. And having this capacity, one then checks that it's equal to the first ECH capacity. But then this means what? This means that we now can get the ECH capacity without any Seiberg-Witten theory. One can really establish this and have a somewhat satisfactory, purely symplectic explanation of what the first ECH capacity means. That's related to a question of, so let me say a few things before time is up. So one corollary is that the C Hopf, because it's a capacity, is less or equal than CZ. I'm going to denote by CZ the cylindrical capacity. Okay. There is a theorem by Edtmair stating that if we talk about the dynamically convex domain, star-shaped, then CZ is less or equal than C Hopf, right? So if you put these two inequalities together, so these two theorems together prove that C Hopf, which is also C1 ECH, is equal to the cylindrical capacity, which is quite a satisfactory statement to have, because this means that between these two capacities, there is nothing else, right? There is a recent result by Abondandolo, Kang, and Edtmair, saying that in the convex case, this C Hopf is equal to the minimal action, which is also quite satisfactory statement to have in mind. They use our results because of this inequality here. So let me just close with the relation between this and a question by Hopf, Wysocki, and Zander. So before the question, actually, let me state a result, which was the topic of my thesis back in 2008. So if we have a star-shaped, my thesis, domain and dynamically convex, then and gamma is a closed characteristic, in the boundary, then gamma spans a disk-like global surface of section if and only if gamma is a Hopf fiber. So this means that the following question, which is due to Hopf, Wysocki, and Zander, can be formulated. I mean, there is a question which I'm going to reformulate in terms of what I've been talking about here. If omega is star-shaped and dynamically convex, is it true that C Hopf is equal to the minimal action? Right? That was answered in the convex case by Abondandolo, Kang, and Edtmair. The original question by Hopf, Wysocki, and Zander was for the dynamically convex case. And so actually the question was about whether the minimal action is the action of a periodic orbit spanning a global surface of section. And that's the same thing as saying that it's a Hopf orbit. And that's why I write here this question as just asking whether C Hopf is equal to the minimal action. So this question remains open. It's answered in the convex case. And right, so I think this circle of ideas basically concludes what I wanted to say. I mean, if there is a message to be taken from this talk, is that knot types might review knot types of periodic orbits, study knot types of periodic orbits. If it's possible to do this with fluor type theories, it probably contains a lot of potentially new dynamical symplectic invariants, and it might shed a lot of light into the symplectic study of the characteristic flow. And so I'll just state one more question slash conjecture. one can hope that C1 is H is equal to the sup right. So I mean, one could, at least for a star-shaped domain, in R4, one could hope that this is equal to the infimum of all over all finite energy foliations, right? So these are finite energy foliations as defined by Hopf, Wysocki, and Zander, meaning that foliations of a certain type, leaves are G0 holomorphic curves with one positive puncture, so on, over the maximum gamma binding orbit of F of action of gamma. So maybe there is a connection between this symplectic invariant and finite energy foliations, and maybe considering more general foliations, one can also hope to define other kinds of symplectic invariants. That's probably all I wanted to say, and I'll stop here. Thank you.
Thank you. Are there any questions?
So you think, so since we also have this result 2 or infinitely many, so then maybe the 2 would always be sort of coming from the Hopf link, and then if you have infinitely many, you have sort of the additional noise.
Exactly. I think so. For a tight Hopf flow in the tight 3 sphere, if there are only 2, we already know it comes from Hopf link. And ideally, right, exactly. So ideally, one would hope that there is always a Hopf link, and well, if this Hopf link is somewhat what we call sometimes, I mean, in the previous work with Almomi and Pedro Salomão, we called, if the rotational numbers are not in perfect resonance, as in the irrational ellipsoid, we call them non-resonant. So if the Hopf link is non-resonant, then there are infinitely many periodic orbits and so on. Even more than that, there is quadratic growth of periodic orbits. And the resonant case would be the difficult one. There should also be infinitely many periodic orbits, but it's not clear how to prove that. So my dream picture of, let's say my dream picture, one possible dream picture for Hopf flows on the type 3 sphere would be that there is always a Hopf link. This Hopf link, either it's resonant or non-resonant. If it's non-resonant, then one knows that there are many periodic orbits, of a certain kind. They already, under this condition, there is already quadratic growth of periodic orbits respect to period, right? This quadratic growth has to be always there, but the resonant condition, the resonant case should also imply that there is a quadratic growth of periodic orbits. So I think that would be a nice, say, end picture for Hopf flows on S3. There is always quadratic growth. There is always a Hopf link. The quadratic growth is there, whether the Hopf link is resonant or non-resonant. So I think that would be, say, the ultimate picture for Hopf flows on S3. At least as far as, I mean, not the ultimate picture, but some satisfying final end for some kind of story about Hopf flows on S3. I mean, for instance, quadratic growth, I think it's always there. I think there is no example of a Hopf flow on S3 for which the following dichotomy is not true. I mean, either there are exactly two periodic orbits or the orbits grow at least quadratically respect to period, for instance. I mean, it would be the Hopf link would be a nice step towards proving this.
Thanks.
Mark, from Felix, you also have a question.
Thank you, Umberto. Umberto, since you expect that there is always a second, I mean, you have a Hopf link, is the action of the second one also kind of capacity-like, or certainly not?
Is this Felix? Hi, Felix.
Yes. Is it maybe C2 ECH or?
I'm not sure. I don't know. I mean,
probably no obvious counterexample.
I mean, I think it might be reasonable to expect that there is some second orbit, right? Which for this Hopf link, which is also capacity like. I think it's. I never thought about this. Thanks for the question, and I think it's quite reasonable actually.
When you have infinitely many, will the second one in the Hopf link be shorter than the other guys? Or is it maybe not so?
I mean, hopefully at least in the dynamically, well, I don't know always, but at least in the dynamically convex case, hopefully the minimal action is a Hopf fiber, and that's a capacity. Should be a capacity. I mean, if it's a Hopf fiber, it's a capacity. That's what we show here, and maybe another invariant, maybe not a normalized symplectic capacity, but a non-normalized one, could be read as the action of the second orbit in the Hopf link. The second orbit in the Hopf link might not be unique, right? So one has to carefully select it. But I think it's quite a nice question.
Okay, thank you. Also for the talk.
May I also ask a question myself?
Hi.
Thank you. So in the theorem you're relating, the previous one, you were relating the C Hopf with the C1, ECH. Now I'm thinking in the case where you have a three-sphere, or in the case where you have a symplectic filling, then you have only two Reeb orbits, and so you could go ahead and compute all the ECH capacities through the C Hopf, if I'm not mistaken. Now my question is there any idea for a generalization of this? So would it be possible to compute the ECH capacity based on the C Hopf more than C1?
Well, I mean, I don't know. It's very hard to guess. As Felix just mentioned, I mean, maybe one can read at least one more, right? At least one more ECH capacity, but to read all of them, it's too much to hope for, I would say. But yeah, I mean, it's I'm not sure.
Thank you.
Can I ask about the proof? So how do you get from the moduli spaces of fast geromorphic curves to the fact that it is the unknotted?
Right. So let me go back to the picture here. So that's basically the proof. So this moduli space, I mean, the slicing disk, the symplectic slice disk is there to say that this moduli space is non-empty. So it's non-empty because one can cook a special J, which turns this which turns a slight perturbation of this disk into a holomorphic plane. And now one has to study compactness. And so the thing is that one looks at space of planes which by assumption are approaching the periodic orbit in a fast way. So this means that, you know, if one starts moving inside this moduli space, let's assume non-degeneracy of the boundary just to simplify things. In that case, we have the SFT compactness theorem to tell us what happens when things break, when compactness is lost. And it turns out that this building, if compactness is lost, there is a limiting holomorphic building. And in the symplectization part of the boundary, there is not enough space for any breaking to happen because of dynamical convexity, right? The top of this holomorphic building will be coming fast to this periodic orbit gamma, but then there is no space for anything else because all orbits have collinear index at least 3, right? There's always some invariance. Sometimes the Fredholm index is enough to say this, sometimes not. One needs to look at finer invariance as defined by Hopf, Wysocki, and Zander. But because the other periodic orbits are also index 3, there is no space for breaking in the symplectization level. And that's why this moduli space is compact. So this means we can put a mark point and start moving this mark point around the interior of this domain. And what happens is that if we take, so this means we can take this, by compactness, we can take this mark point everywhere. And now we start pushing it towards the boundary, say, towards a point in the boundary, along a point in the boundary which doesn't go through any periodic orbit, which is the case, for instance, if you have non-degeneracy on the boundary. You can always find such a point. And you move this point over there, but then assume by contradiction that the plane never enters completely into the symplectization part near the boundary. There is always a piece of the plane which is touching some compact region inside, right? So this forces breaking, this forces a non-trivial holomorphic building in the limit. And this is precisely what dynamical convexity prohibits from happening, because the only possibility for an SFT limit here is just another plane. So one forces breaking by taking this point and pushing it towards the boundary along a direction that goes to a point which is out of the periodic orbit, under the contradiction assumption that some part of the plane is always touching some compact region in the interior. So this gets us a contradiction, which means that the plane eventually goes totally inside the symplectization part, this R-invariant part of the symplectic completion of this domain. And now we're in business, because now the plane started embedding, self-intersections never develop by positivity of intersections and so on. You have to use intersection theory here. For instance, one can use the results of Vinicius Siefring. And yeah, that's how the proof goes. Of course, there are details, right? But the main thing is that dynamical convexity doesn't allow for non-trivial holomorphic buildings to show up.
Thank you.
Okay, so let's thank Umberto again, you.